Cambridge AS Computer Science Chapter 4 Processor Fundamentals Assembly Language. Eh, We did that before. We did that before. We know that assembly language, there is an instruction set. Okay? That instruction set will be given in the exam because every processor has its own instruction set. This makes solving questions easier because you have a list of instructions you may use or you need to understand. However, you need knowledge about addressing modes, you need knowledge about how to trace a program written in low-level assembly language. And also, there is one little new topic that is called bitwise manipulation that deals with single bits, for example, and or, for example, shift left, shift right. These are new and very easy, and they show many times in the exam. Okay, so this is an example of an instruction set. Last time we were in that instruction set. We studied that before. Okay, let us go now to an example. The following table, so this example is copied exactly from an exam. Okay, the following table shows an assembly language instruction for a processor which has one general purpose register, the accumulator. You know that the accumulator is a general purpose register. Other registers are special purpose registers. LDD comes with an address. This is direct addressing. Load the content of a given address to the accumulator. STO stores the content of the accumulator to the given address. So it is doing the opposite. Store is storing. LDD is loading. Okay. LDI indirect addressing. LDX indexed addressing. Okay. INC add one to the content of the register ACC. JMP jump to the given address and return control. Okay. Okay. So this is the instruction set given. Okay. The diagram shows the contents of the memory. So this is the content of the memory. Okay. So address 120 has this value. Address 121 has this value. Okay. The contents of the accumulator after execution of the instruction LDD121. So the question is asking you to show the content of the accumulator after executing this instruction that is LDD. You have to go and see that LDD is direct addressing. Load the content of the given address to the accumulator. Okay. So LDD121, you go here to 121, you find this content and you load this content into the accumulator. Okay, you earn 1 mark there. Okay, easy, but with understanding and knowledge about accumulators and memory addressing and all the topics we have discussed. Okay, the second question is the content of the accumulator of the execution of the instruction LDI 124. What is LDI? LDI is indirect addressing. The address to be used is the given address. Okay, the address to be used is at the given address. Load the content of this second address to the accumulator. Okay, so you have LDI. Okay, you have LDI 124. You go into 124 and you find this value. Okay, okay, immediately you convert this value into denary. So this is the explanation of the above result. Explanation for the above result. The content of 124 is 0111. You go to 124 and you find this address. This is equivalent to 127. You change it into denary immediately to become 127. The contents of 127, you go to 127 and copy this value into the accumulator. Okay, so the answer would be this value together with the explanation. Okay, Next, the content of the accumulator after execution of the instruction LEDX 120. What is that LEDX? Indexed addressing. Form the address from address plus the contents of the index register. So here you need to know the contents. Here you need to know the contents of the index register. Copy the contents of this calculated address to the ACC. Okay? Okay. The IX should be given. So this is the IX. The IX holds the value 110. You should immediately convert this value 110 into 6. Okay? So the contents of the IX is 6. And you have here LEDX 120. So you add 120 to 6. So this is 126. And you copy that 126 into the accumulator. Okay? And you also have to give that explanation. Then you need to trace the assembly language program. You do dry run and create and fill a trace table. Dry run and fill a trace table. Okay? So this is a program. However, that program is written in low-level assembly language. Okay? So you have 300. LDD 321. LDD 321. Okay, let us see what is the meaning of LDD. LDD means direct addressing. Load the content of the given address to the X accumulator. So LDD 321. You go to 321 and the value in it is 36. So you put here 36. This is the trace table. Okay, so 303, the memory address 321 has 36, so you copy that 36 into the accumulator. Okay, then INC, what is the meaning of that INC? INC means increment. Add 1 to the contents of the register ACC. Add 1 to the content of the register ACC. Okay? Okay, so you increment that 36 to become 37. Okay? Then the instruction after is store, which means stores. To store the content of the accumulator into 323. So that 37 will go into the memory address 323. Okay? And then LDI 307. What is that LDI? LDI means indirect address. Okay, so LDI 307. Okay, you go to 307. LDI 307. You go to 307 and you find 320 in it. You go into 320 and you find 49 in it. You copy that 49 into the accumulator. Okay, then what? INC increment, the accumulator becomes 50. Then what? Store 320, you store that value in 320. Then what? End, then the program ends. Okay, very simple if you know meanings and addressing modes associated with a low-level assembly language. Okay, okay. So another program that would be a little bit more complicated. Okay, so this is another example, and here is another example. Okay, and afterwards come bit manipulation. Okay, let us study bit manipulation first, and then because they are very easy, let us study bit manipulation. They are very easy, and then we go and practice and end this chapter. Okay, let us first study bit manipulation and spend the rest of the time with the left two examples. Bit manipulation, what are the bit manipulation commands? We have binary shift. You already know shift left and shift right. Okay, logical, arithmetic, and cyclic left shift, cyclic right shift. Okay, so these are the examples of bit manipulation. Manipulation can be used to monitor and control devices. You can monitor a device by reading if this bit is equal to 0, if this bit is equal to 1, and then you can decide the action. Okay, carry out bit manipulation operation, test a single bit if it is equal to 1 or not, or set a single bit into 1 or 0, or using bit masking. We have to know all these skills. Okay, so we have another instruction set for bit manipulation, and that bit manipulation is new to the topic, and and it comes quite often in exams. Okay, so we have and hash n, so that hash n is immediate. Okay, so bitwise AND operation with the content of the AND with the operand, because this is immediate. Okay, you know, things that come with a hash, you just use the value. So this is bitwise, means every bit is AND with its corresponding bit. Okay, and comes with an address without the hash. This is add. This is direct addressing. Okay, so this is direct address. Bitwise AND operation of the content of the ACC with the content of the address, because it is direct addressing. Okay, XOR, you do the XOR operation. Okay, XOR operation immediate, XOR operation direct. Okay, or you do the OR operation immediate, or OR operation direct. Okay, you know these. LSL is shift N with LSL with a number. LSL with a hash number. Okay, bits in the accumulator are shifted logically N places to the left. Zeros are introduced on the right hand end. So logic shift left, the LSL comes from logic shift left. You lift bits to the left, and you fill on the other side empty bits with zeros. Okay, LSR يبقى logic shift right. You shift to the right and you fill on the other side empty cells with zeros. Okay, so this is an example of bit manipulation. Let us do this example. Let us stress more on these, because they show more often in exams right now, and they are very easy. They are easier than tracing assembly link. Okay, a machine has machines. Machine has a count. Record the number of cake tins filled. This is typically copied from an exam. Okay, each time a cake tin is filled, the counter is increased by 1. We want to see the values. The value is stored in 8-bit register. The current value is shown. Okay, so this is the current value of the register. We want the value of the binary number after another 5 cake tins have been filled. Okay, ماشي. This is found by adding 5 to the binary binary to the value in the register. Okay, so this is the value in the register. This is the original value of the register. And you want to add 5 to it. Okay, so what is 5 in binary? You have to convert them really fast. 5 in binary is 101. Okay, you have to do binary addition. So 1 plus 1 is 0 and carry 1. Okay, the carry 1 plus 0 plus 0, here is the 1. Okay, 1, 0 plus 1 is 1. 1 plus 0 is 1. 0 plus 0, okay. So this is the new value. Okay, the assembly language is okay. So that was the answer. The assembly language statement to reset the register 0 is we want to reset all this to 0. So the assembly language statement to reset the register to 0 is and hash 0. So this is the answer. Okay, we can put it in a new line like this. Okay, and hash 0, because you want to make them all into 0, and when you AND with 0, everything becomes 0. Okay, so this is the assembly language statement to reset the register to 0. Okay, okay, a two-place shift left to a two-place logical shift to the left is performed on the original binary number. So let us get back the original binary number. Okay, before adding 5, the result of this logic, this is the value before the logical shift. 5 places to the left. Okay, 2 places to the left. Okay, so after shifting, this goes into here, and this goes into here, and you fill empty space or empty places with zeros. Okay, so with logical shift, you fill empty places with 0. Okay, okay, next. That was an exam, I think that was specimen 21. Okay, the mathematical result of one place logical shift to the left of the binary number is multiplying by 2. So when you shift one place to the left, this is multiplying by 2. The mathematical result of one place logical shift to the right is division by 2. Okay, okay, let us go on. Easy questions, easier than tracing and dry running. And I think those questions will appear often in your final exam. Okay, look at this question. The current contents of main memory is shown. Each row of the following table shows the current contents of ACC in binary and the instruction that will be performed on this table. The new contents of the ACC after execution of the instruction. Okay, so that's the question and the answer. So this is the contents of memory. Address 100 holds this value. Address 101, 102. Okay. The current content of the ACC is this. And the instruction is OR 101. That was the question. When you OR with 101, any one will remain 1. So after performing OR 101, this becomes the rest. Okay? Okay. The contents before operation is all 0. And you XOR. Let me tell you a hint about XOR. And you XOR hash 15. So you don't go to memory. Hash is the value. 15 is the value. Convert 15 into binary directly. immediately. So 15 is 1, 1, 1, 1. 0, 0, 0, 0, 1, 1, 1, 1. Okay? And when you XOR, okay, XOR with a 1 toggles. XOR, so when you XOR with 0, the value remains the same. So this is the input. And when you XOR with 0, the value remains the same. When you XOR with 1, the value toggles. So 0, 0, 0, when XORed with 0, 0, 0, remain the same. 0, 0, 0, 0, when XORed with 1, 1, 1, 1, the value is toggled, and this is the result. Or do it anyway. Do it anyway to know the result, you know, the XOR and how it operates. Okay, this is 1, 0, 1, 0, 1, 0, 1, 0, LSR, which is logical shift right. Hash 2, 2 places to the right. Okay, okay, shift them all 2 places to the right and fill the empty locations on the left with zeros. This is logical shift right. And this is the value before the operation. And the operation is AND 104. What is that one? What is the value is this? So 0, 1, 0, 1, 0, 1, and with all zeros, and the result is all zeros. Okay, that was an easy example. Okay, and these questions, they are the questions that will appear in your exam, inshallah. Okay, next, well, how many questions do still we have? Only 1 or 2 examples, and we go back to that tracing. Okay, I know tracing is more difficult, but we have to go back and study these, and the rest will be left for you as a home. Okay, another example. The table shows part of the instruction set for a processor. The processor has one general purpose register, the accumulator ACC. Okay? Okay, and a binary number, bitwise AND operation of the content ACC with the operand. XOR with a binary number, or with a binary number, and XOR, and this is the binary number. B denotes a binary number. So no referral to memory. This is immediate. The binary value is stored in the memory address 20. Okay? Each instruction in the diagram is performed on the data on memory address 20. Okay? The a line from each instruction to its correct. Okay? So when you XOR this with that, when you XOR this with that, when you XOR with a 0, the value remains the same. When you XOR with 1, the value toggles. This is the easiest way to deal with an XOR. So 1, 1, 1, 1, 1, 0, 0, 0, 0. When you XOR with this, the first part remains the same. The first part is toggle. 0, 0 is toggle to 1, 1. And 1, 1 is toggle to 0, 0. Because you XOR with ones. And here, XOR with 0, it remains the same. Okay? So you perform XOR and connect this to this. Or, when you OR, anything that has a 1 remains as a 1. So you OR this with that. Okay, it is so full of ones, like this. Anything that has a 1 remains as a 1. When you AND with this, anything AND with a 0 remain a 0. Okay, so when you AND with all ones, it is like when you copy this into here. Okay, easy marks. Okay, that's the end about bitwise manipulation. We go now to the 2 tracing scenarios. Let us do them and end with this topic because you have loads of examples to do in the classified. Okay? Okay. Let us go to here. We did that. Let us go to this. Example. The table below shows assembly language instructions for a processor which has one general purpose register, the accumulator, and an index register, IX. LDD, STO, LDI. Okay. The diagram shows the current contents of a section of main memory and the index register. This is the index in case. So address 60 has this value. Address 61 has this value. The contents of the accumulator after the execution of the instruction LDX60. So what is LDX? Indexed addressing. Okay. So LDX indexed addressing. Okay. Copy the contents. Okay. Okay. LDX 60. Okay. Okay. So you go to 60. 60 has this value. Okay. The accumulator has this value. The contents of the IX is 8. This is the index register and its value is 8. Okay. The content of address, that is 60. 60 plus 8. This is 68. You copy this value into memory. Okay. So the 60 will be added to the 8 in the IX, and this will refer you to address 68. You copy the 68 into the accumulator. Okay. The contents of the index register after the instruction DECIX. So you have the instruction DECIX. So DEC means decrement. IX means subtract 1. The IX used to hold 8. After decrementing, it will hold 7. Okay, so now the IX holds 7. Okay, tracing. Let us do the tracing of this algorithm. Okay, LDD 100, add 102. Okay, so LDD 100. What is LDD? You have to go here. LDD is direct addressing. Wrote the contents of the given address to the ACC. So LDD 100. Okay, go to 100 here. Go to 100 here. 100 here has 20. So load that 20 into this. So this is the trace table you should be doing. So load the 20 from location 100 into here. So the 20 will copy to the accumulator. Okay, next, add 102. So what is add and 102? This is add. Okay, add 102. So you go to 102. This is 102. It contains 1. You add it to the accumulator. Okay, and then store 103. You store whatever in the accumulator in 103. Next, LDX 100. What is LDX? LDX is indexed addressing. LDX is indexed addressing. Okay, so you load. You should be given the the index is by 1. So here LDX 100. So 100 plus 1 is 101. Okay, so you load that 101, that is 100, and you put it here in the accumulator. Okay, and then add 100. Okay, so you add 100. 100 has 20. Okay, it becomes 120. And then CMP 101. This is a comparison. CMP is a comparison. Compare the address ACC with the contents of the address. So you compare ACC with the contents of the address. Okay, so you compare 101. So you compare the accumulator with the contents of 101. This is the accumulator, 120. Compare it with 101, and this is 100. So they are not equal, but there is nothing to write. So in instruction 55 is you have a blank line here. In instruction 55, you have a blank line here. Okay, and then, but remember that the last comparison now is not equal. Jump if equal, but the last comparison is unequal. So jump if equal. So don't do that jump. Jump 58, don't do it because the last comparison is not equal. So 56, the command 56, nothing to do with it. Okay, next, jump if not equal. Yes, the last comparison was not equal. Jump to 59. Okay, however, here 57, there is nothing. However, after 57, you're going to do 59. What is that in that 59? 59, I increment the IX. Okay, so increment the IX. The IX used to be 1. Now it becomes 2. Okay, increment the IX. The IX used to be 1. Now it becomes 2. Okay, we are about to finish. LDX 98. You know that this is indexed addressing. 98 plus 2. So LEDX 98 plus 2 becomes 100. So you copy the contents of the 100 into here. Okay. Add 101. Okay, you add the 101. Add 101. Add 100 to the 20. Okay. Add 101. And then out. Let us study that out. Remember now the accumulator now has 120. Command out sends output to the screen. However, the value is converted into its character, considering that value as the ASCII code and finding the character corresponding to that ASCII code and shows it on the screen. So when you out 120, please notice that you are provided with a part of the ASCII table that you will need. That was given in the exam. So 120 is X, you output that X on the screen. You may wish to put it between quotation, that would be better. Okay, so that was an example. That was a very good example about tracing a program written in low-level assembly language. You have loads of questions like this to go through in your classifier. Okay, let us go through this as well. This is taken from example 20, June paper 1-2, question number 5. The table shows part of the instruction set for a processor. The processor has one general purpose register, the accumulator ACC, and an index register IX. Okay? Okay, we are familiar with it. We will refer to it when we need. The trace table for the following assembly language. That was the question. On the left was the question. On the right was the answer. Okay, so this is the answer. That was the question. This is the mark scheme. So address 20. Load 103. Okay, so what is LDD? LDD. Please forgive me that not everything is written here, because the time I was creating that question in the notes, I didn't copy everything. We can go to it in the past paper. So actually, this is the complete instruction set in the exam that actually I didn't copy all into my notes. Okay, we can refer to here to have the complete set, because this is the question and this is the trace table you are supposed to fill. You may wish to go to page 224 in the classified and give yourself some times now to solve it, and I will check it with you. Okay, so the trace table for the following assembly language. LDD 103. Okay, so let us go to the instruction set. LDD direct addressing. Load the content of the location at the given address to the accumulator. Okay, so LDD 103, that 130 will be copied to the accumulator. CMP compare. Compare the contents of the accumulator with 101. Some of the instructions I already memorized. Okay, because compare only comes with direct addressing, I think. So CMP compare the accumulator with 101. Comparing with 101, 101 holds 2, and the accumulator holds 0. So the result of comparison is not equal. Okay, jump if equal 30. No, they are not equal, so do not do that jump. LDD 100, so you load 100 to the accumulator. Okay, add 101, you add 101 to the accumulator. 2 plus 1 becomes 3. Store 100, you store the 3 into 100. Okay, INC accumulator, store load 103, you copy the 103, the 0 to the accumulator. Okay, INC the accumulator, increment the accumulator by 1. Okay, store 103, you store the 1 in 103. Jump 20, you jump to 20. Okay, so this looks like a loop. Jump to 20 looks like a loop. Okay, so we can use jump and instead of a loop or instead of selection if then else. You will be doing this in the A2 inshallah. Okay, so jump 20, you go to 20 and the program repeats. LDD 103, so you are now doing address 20 again. You load 103, you load the 0, LDD 103. Okay, 103 now has 1. It doesn't have 0 anymore. 103 now has 1. So you load the 1 to the accumulator. CMP 101, you compare the 1 with 101. So you compare 101. Okay, you compare that one with 101. No, they are not equal. Okay, they are not equal. Jump if equal, no. Load 100. So you are doing it again. Load 100. You put the 1. LDD 100. Okay, you are now here 24. You load 100. Okay, load 100. You copy the 3 into here. Okay, add 101. You add the 101, the 2, and it becomes 5. Store 100. You store the 100 in here. Okay, load 103. You load the 103, the 1 into here. Increment ACC, you increment it into 2. Store 100, you store the 2 into here. Okay, ما هو دلوقتي now jump store 103. Okay, jump 20. Jump 20. You go to 20. Load 103. You load You load 103, you load the 2 into the accumulator, compare with 101. So now the accumulator has 2. Compare with 101. 101 has 2. So the result of comparison is equal. Jump if equal 30. Now you jump to 30, and 30 is end, and then the program ends. Okay, so that was the end of chapter 4, processor fundamentals, talking about assembly language and creating the truth table and dry run for assembly language program. Thank you very much for your attention.